Okay, guys, I think we're going to start. It's working now. Okay. Yeah. First of all, I'd like to thank each or every one of you for attending this meetup. So really appreciate you guys taking your time out from the busy schedule, especially after working hour. Allow me to introduce myself. My name is Jeffrey. I'm one of the organizers of this Rust Meetup Malaysia, together with Ivan over here. So Ivan has been doing this for quite a few years. So yeah, from time to time we have Rust Meetup like every 2 months. So today, our main agenda, we will have a talk by zypeh about uring. Right. So again, appreciate for you to willing to give a talk and all the effort and preparations. So before that, before we get into the topic, we'd like to spend some time in last corner talking about some recent update in Rust. This is our social media. So you can mainly find us in the Telegram channel. I think most of you in here joined in the Golang channel, but we do post some updates about Rust in the channel as well. And we do have a Rust Malaysia Facebook group, Rust Malaysia Facebook group. It's not very active, but time to time we still post some upcoming updates on events, workshop. Yeah, so if you guys want to update, if you guys are interested, can join Rustlang Malaysia. And okay, so first of all, let's start with Rust 1.07 versions, which is being released, I think, last month. Right, so there are some key updates in this version. One of them, the first one is sparse by default for Crate.io, right? So if you guys know sparse, right? So basically, in short, should I explain? Should I explain? You guys interested in sparse? Okay, I explain. So basically, there are something called cargo, which is a backend manager for Rust. This is like npm for JavaScript, right? So whenever cargo try to install a package into your local machine, you run a program, right? You will first need to verify the version and dependency that you use in your program. So how it does is you actually download the index of all crates, which is all the packages. Right, so all these index actually hosted in GitHub repository, which is in the old way. So every time when you try to run a Rust program, you actually sort of like git clone down the whole copy of indexes in your local machine. So with this actually causes some issue is when the index grow, right? And because every day you got people publish or update their versions, right? And when you download or update your local crates index, it will take longer time. So when you try to deploy in your CI/CD, it will take a lot huge amount of time. So with Sparse, right, they actually changed it's sort of like an indexing protocol. So the way they actually enhance this process is like instead of using git clone or downloading indexes, they're using HTTPS. And all these Sparse index are actually stored in a file system, which you can access through like index.crates.io. Yeah. So previously in 1.6 something version, if you want to use Sparse, you have to explicitly config. Right now in this latest version, it comes by default. Okay, so basically this is about Sparse, and then we have one cell, one slog. It's basically started with a community-driven packages. Basically, in short, allows you to create some sort of like global variable in Rust, right? So one slog is a counterpart of one cell. One slog is multi-threaded, thread safe, and one cell is for single thread, right? And so in this version, they stabilize both of these grades and they add it into the standard library. So you do not need to install using one other packages. I can use it straight from the standard library. And then we have some method called isTerminal, basically. One trait called isTerminal, basically just to differentiate whether you are in running script or you are in interactive mode. Right? So it's helpful if you are working on TUI, right? So yeah. And then we have another version of Rust 1.71. So some key updates here is a debugger visualization attribute. So this is sort of like a new attribute that you can add which support Navis file. So Navis file is sort of like a script used by Visual Studio Code for debugger inspection output. Right? So right now they support it. So this file is actually contain a format of what kind of output when the user inspect the data structures. What is you can customize the format. So right now you can add this attribute. And then we have const initialize trait locals. Basically, you can use const block to initialize variables inside your trade locals. So, but this feature actually has been a while in Rust. It's just that they didn't add it into documentation, so a lot of people are not aware of it. So in this latest version, they add it into the documentation stuff. And then we have Bevy 0.11. If you guys don't know, Bevy is open source Rust game engine, right? So it's written fully in Rust, and they had a lot of new updates in this like 0.11 versions are like performance improvement, right? Who don't like that, right? So if you guys are interested in Bevy's game development, feel free to go and have a look. So Polars, yeah, some exciting news in the Rust community, right? More job opportunity if you guys want to be a Rust developer. So we have new open source, started as an open source company, right? Just 3 years old open source company, and they recently raised 4 million, around 4 million of fund, and they started a company called Polars. So in short, Polars is sort of like the alternative to Python data frame. So if anyone in this, sorry, Pandas, yeah, Pandas. So alternative to Pandas in the Python. Polars. Yeah, Polars. Yeah, it's called Polars. So you guys are in the data space, right? You might use pandas, right, frequently, especially for data scientists, right? So these are sort of an alternative to that, but it's written in Rust. So we had inherit all this performance from Rust, and it's leveraging Apache Arrow in-memory data format, all those kind of stuff. So yeah, it's pretty cool. You guys can try it out. It's really amazing.
Can I explain a bit more? Yeah. So for Polars, what's the difference? Watching from YouTube might be interested. So Polars is a bit different from Python data pandas, as in Polars have the ability to have the lazy data frame, because pandas is always eagerly loaded. When you load, everything goes to memory. But Polars, their design from scratch is the design is a bit cleaner, as in because the API they take from previous existing experience in pandas. So the API is not as confusing as pandas, but the API is simpler and more straightforward. A bit longer to write, but a bit more straightforward. And the API is available in Rust, in Python, and then in JavaScript as well. So one difference is that the lazy evaluation, as in the Polars, you can load partly in memory. So it doesn't load everything into memory. It can go through your data lazily, like go through row by row, something like that. And another benefit of Polars is that Polars is able to use multiple threads easily, because it's designed from scratch to do like the multiple threads and make it faster. Multiple threads or multiple processes, I'm not sure, but it can run parallelly. That's why it's faster and then more like less memory use. But compared to the integration of pandas, maybe it's lacking a bit right now, as in it doesn't really integrate with like the TensorFlow and those kind. But you can use it like pandas replacement if you just use pure pandas. Yeah. And switching between the eagerly loaded Polars, the data frame, and the lazily loaded, it's just like one line. So just one line, then you can just make it lazy, and then one line, then you can like performance like jump. That's what's interesting about Polars.
Very cool, and still very young, only 3 years. Okay, the next one is Zcash. It's something in the crypto world, Web3, right? So Zcash is basically, my understanding of it is like the point, but with privacy implemented. Right, all the transactions are actually public, right? So some of the scientists, they saw this as an issue. They forked Bitcoin early, and they added these privacy features, which actually encrypt all your personal financial information. So basically, itself is a cryptocurrency, and they have their own network. So they recently, I think they released their Zebra, which is like their node, the node in their network. Right? It's written in Rust, the whole thing. So yeah, so if you guys are interested in cryptocurrency Web3 and interested how they implement Rust and writing you guys can have a look. Okay, so the next one is a Diesel 2.1.0. So Diesel, it's a query builder ORM in Rust, right? So who say Rust is not suitable for web development, right, for backend, right? Basically, you have everything, right? You have Exum, web framework, you have Diesel, all this kind of stuff, and even have Dioxys, right, for front end. So we can basically do the full stack using Rust, right? So what's interesting in Diesel 2.1.0 is they release a new CLI features, migration features, where you can migrate your script, generate the SQL script based on the Rust local Rust schema. like you define your local Rust struct and then you run this diff script, it will check the difference between your database schema and your local Rust schema, and then it will generate the SQL schema for you. Then you can run and migrate in your database.
I can explain more a bit about Deezer. Deezer is like an ORM, but the concept is more like towards it's not like the active record pattern, but more like towards the data. What was the other pattern? One is called data mapper. It's more towards the data mapper pattern, and it's similar to. It structures it in a way that the code looks similar to how you write normal SQL, except the API, because Deezer is type safe, so when it compiles, right, the SQL query will work. And one thing I like about that is that because as you write the code, then the compiler will compile the code for you. It's like you run a lot of functions like this table dot insert dot something, and then the compiler compile, right. When you compile, then you know it works. And it's just using the normal function, although it has some code generated in the back. And one alternative to Deezer is we call it SQLX. SQLX is a bit more towards writing raw SQL. SQLX, one thing interesting about SQLX is that it's an alternative to Deezer because some people might not want to write ORM because it's tied down to the platform. Although I find Deezer quite interesting as in it solves a lot of issues with other ORM, as in other ORM sometimes you write edge cases code that is not in the documentation, then you cannot imagine what will happen. Then you run it and then why does it work like this? It's supposed to work, right? Then you are expecting it to work, but sometimes it doesn't work. But Deezer everything they encoded in the type. So the query, join, left join, those all they put in type. But there's downside to that. The type when you look at the documentation are very confusing. The types have many things joined together. That's a downside. But then they do it the type safe not just for Postgres, they do it for multiple databases also. They do it for Postgres. So Postgres supports certain syntax. Then Deezer will support the type for that. Like let's say you can use upsert. I think you can use upsert in one or two of the database. Some other device you can use upsert. And Deezer put that in the type as well. So in type when you use a SQL database, you can't do upsert. So I find that quite interesting. And the SQLX is the alternative to Deezer that you write raw SQL. The difference, the SQLX have an interesting idea is that SQLX you test the query against your database during compile time. So when you compile, you test whether the query will work or not. Yeah, that's one part I find quite interesting because a lot of time, right, when you write the SQL query, you doesn't know whether it will work or not without running it. But SQLX will run it
during compile time.
Yeah, during compile time, which is
very dangerous.
It's very important.
If the interns write some malicious or some
then we have a production issue.
Delete table, compile time, delete already.
You compile, you execute on the database,
An interesting function database.
Yeah.
You just test again the schema. I think probably goes to the database and then check the schema. I'm not sure whether you run or not, but I think it's something.
For the reference, because just now we talked about test the query before execute the database. Like let's say you update and update and when we actually when in the testing we do the actual with your DB for testing on its own. The question is the test if let's say we delete, then it really if the query is successful, then the actual data is delayed. Then
You mean like run something?
Yeah, I think it's a dry run or something like that. I didn't run it on production, but I think I tried it out. It's like something like that.
It really didn't affect the database.
I don't think you did.
Maybe you just compile. In terms of like maybe there are some checker really check in
Transaction or something.
but it doesn't affect. Like maybe compilers of SQL or something. Yes, you validate whether you have typo in your query or anything. I think something like that. It does not really.
And the type also, and the type whether you put in the type is correct or not. Because your type you need to convert to the SQL, right?
Because EF code doesn't have any compiler support. You have to run
Yeah. Okay. Yeah.
You can do so you can create a transaction and then end it with rollback. It won't actually execute anything, but it will validate.
Validation. Okay. Yeah. Cool. Yeah. Very good. Hmm? Oh, then the last one is just some updates in the community. There are some proposals with crates IO policies. So this actually caused a little bit of drama in the Rust community itself. So they actually try to tackle one of the problem we found in the crates itself, name squatting. So people actually reserve the name, they publish the packet, reserve the name because we don't have namespace in Rust crates, right? So if you use the name, right, it's first come first served matter. You can't. People use this name if you like XXX, and people already publish package XXX, you cannot use it. So there are some people like purposely doing this to reserve name, and then you need to do a lot of stuff like ownership transfer, right? So basically, they come up with a new policy to tackle this problem, saying that if they found you are not actively developed, right, on your published packages crates, right, they will consider you like against the policy. Maybe they can delete your crates. So this, I think namespace kind of solve these issues, right? Like how Ghost does it, right? You can have my name Jaffilian slash Tokyo, right? Then you have everyone can have their own Tokyo, right? Just using namespace. But I'm not sure why. I think there are proposals on namespacing as well. So let's see how it goes out. So if you guys are interested in this topic, can go in there GitHub pull request. Yes. Yeah, yes, exactly. Like, how do you define, like, okay, you're actively developed? What if the guy went to hospital a few months, cannot develop, right? So yeah, so basically that's it. Basically that's it. Rust Bus corner. So we have finished the
Yeah, so we
update.
have the slides here.
Yeah, if you guys are interested in the slide, can download the slides, scanning QR codes. Yeah. So now, pass the floor to that right. So let's go to our main topic over here today. IO uring, right? And a lot of the ring.
About the ring, yes.
Yeah,
So
if we still have time, maybe we will talk a bit. We'll have some talk about enum in Rust algebraic data types because maybe we can learn something new from beginners. Yeah.
hey, I should share my screen. I should share my screen here with this cohort. Let me share my screen. Should be this screen. Full screen, custom, critical source. Okay, let me see. Favorite screen should be, I think it's back to text. Oh no, custom. Should be this, right? Second one, favorite go live. So yes, there you can actually see my screen. Okay. So, is anyone familiar with the IOU ring? Or even heard of the name of? Yes. Yes. So, you may go. Okay, no problem. So, my talk, you may echo. I think you can just. Yeah, okay. So my name is Zheng Yan. You can see the ZY there. That's my initial name. So what I do is I am a software engineer. A software engineer working in an automated trading firm. So me personally is coming from functional programming ways. And functional programming, yeah, I see someone is the level of functional programming. He keep moving his arm. Yes. So previously I am writing Haskell and all this. So when we are writing Haskell, we are conscious about the runtime and all this. But because of the nature of the language itself, it handles all of the I/O and how the language act with the real world like I/O. So that is why the name called I/O. And the uring, later we'll explain to it. The IO uring is a Linux specific new a new mechanism to help you to do all this I/O in an asynchronous way. So whenever you want to send a packet in a network, you want to write to a file, you want to read a file, anything that the machines needs time to actually does it to process it. Even if you are moving some memory from one end to another end of a OS kernel, it also takes time. So I am the one who will be presenting the IOU ring and explain to you in depth on how IOU ring works and what is the use case of it. So me, I am an electronic trading enjoyer. Why? Because it tackles a lot of problems where when I am working in a startup, doing all those CRUD stuff, endpoints and all this, and database schema, I find that doing the electronic trading and like automated trading will actually gives me a lot of experience and a lot of problem. So what I do in my company is I do HPC stuff. HPC stands for high performance computing. So we deal with low latency manner of code because the market is so fast. So we have to act fast to actually process this. And then we not necessarily need to be fast. We need to be low latency because market sometimes can be inactive. Sometimes it can be very active. So we need to process these packets as fast and then as responsive can. So most of the time when you heard about electronic trading, it should be buy low, sell high. I mean, how do we earn money? Yes, we do buy low, sell high. That's how we earn money. And then one of the way we want to earn money is actually doing arbitrage. You act faster than people to buy things in a cheaper way, and then you act faster than people to sell it in a higher price. So that's how we do. But a bigger chunk of our life as an electronic trader, we are doing market making. So that's why I need to explain to you what is market making. So let's say if you are a Lord of the Ring fan, if someone wants to buy something in real life, not in Lord of the World, not in the Middle Earth thing, in the real world, if you try to buy something, and then if there is no seller, what will you do? You can't do anything because there is no seller to sell you things. So that is someone needs to be responsible for selling you things to make a seller and all these things. So in order to have this kind of trades happen, you have to match these two orders, buy and sell things. So a market maker comes up is the one who doing like a supermarket. He hold the inventory for you and then to sell things. Yeah. So the risk they got is the inventory risk because you buy something and then you need to sell it. You hold it, you need to hold it, and what if the price drop and then you have to sell it? Means that you buy high and then you sell low. That is the thing. So what we do is we provide the liquidity because someone, if they want to sell things, they don't have a buyer, then how? We provide the liquidity in the financial market. And then second thing, where in software engineer perspective, it's our requirement also. We are highly sensitive to the price and the offer price of the market. So we need to keep eyes on it. We need to listen to a web socket of it from the exchange. There will be a market feed coming toward us, and then we need to process it and all this. So that's what we do. For the price update, if you want to do the cross exchange, they got at least 3, okay? And then for those assets, if you want to process multiple assets, you must have multiple WebSocket of it from different exchange, from different endpoint, maybe from different data center and all these things. So we have to listen to, for every trade, we have to listen to all the change stream or the book stream, and then once you execute, it got the update to us, the execute stream. So the crypto exchanges will make a lot of WebSocket connections. So this kind of connections, it may be easy when you are doing in Node in an asynchronous way, but if you are conscious about the latency, it may be a problem, because let's say you have hundreds of WebSocket connections, and then you are keep pulling the sockets to see if there is an update or not in the system way. In the OS, you need to keep pulling it and all this. So for us, sorry. So for us in Rust, there is one library called Docker. For Docker, it is the de facto implementation in Rust. So when you are in Rust, people will talk about asynchronous. There's only one mainstream implementation, which is Docker. It almost monopolizes the whole ecosystem. And then for Rust, yes, we do have a syntax for the asynchronous programming. That's the async and await, just like the JavaScript. So so people who write JavaScript will find the Rust is actually quite interesting, familiar, because we do have the async and await. And for function that requires you to await things, you have to carrying it. You need to prefix it as sync. So this is a sync function. Inside it, it can use the await. So what does the async await does is, you inside await, you purposely tell the OS, tells the program to wait for it to happen. For this, is a synchronous block. Whenever you use the await thing, the process won't be processed until there is a WebSocket connections packet coming in. That is what you do. In the async, the receive method is actually a sync function. That's how you can await it. So you await it, and then if there is some message, then you process the message. So why will people use the Docker usually? Just like what you do in JavaScript. You want the task to be you want the asynchronous functions to be working as sequence. You await things so the next thing won't be happen before this one finish. So this is how you do. Wait, yeah, the wait. What? Okay. Don't forget. Oof, don't forget. The await is actually not a method, it's a syntax of await. Something like that. And yeah. So, wait. Okay, the third point here, the goal here is to eliminate the OS thread. There's one thing that works similar to this one, which is the OS thread. So you spawn the thread, it can actually work in the background. But in here, the Docker is actually user space. Why is that? Because if you receive the thing, does anyone knows how Docker works? Alright. I think I'll just explain the OS threads and the Docker thing. So, if I am the one who write the OS thread, imagine a world without a Docker and without a sync. So we will spawn an OS thread, and then it will do the receive thing. And then once the receive actually finish, how do you know it finished? You keep pulling it. There is one system called, in C language, you need to tell the OS to pull the data from this file descriptor. Because you establish a web connection, you get a file descriptor. Whenever you open a file, you get a file descriptor. It's a file in OS that this is the handler of this task. So you can deal with this task. This FD is an unsigned integer number. You deal with this, then you get this thing. Bring it. In Docker, it not necessarily needs to pull it. Why? Docker do have two components. One is executor, one is a waker. Waker will pull for you. It actually will listen to the OS, listen from the event FD, which is another file descriptor from the OS. It not necessarily has to pull it because the OS will tell you this, notify you, and then the waker will wake up this Docker task. This Docker task, and then it will happen, telling you this away, and then you can process it. So what we do when we got multiple web socket connections, because let's say we listen to two web socket connections, and then the frequency is different. One is 1 minute per update, and then another one is 2 minutes per update. Then you will blocking until the 1 minute. Because it's blocking, because it's blocking, so you need to blocking and then wait for it to happen. And then until the next line of this loop, you need to wait another web socket connections happen. So what we will do is we have a Docker spawn. We spawn this async task. Async move tells us that this is a computation that will be moved to a Docker trace with Docker spawn 1, and then that is the computation we do. So in the line 1, which is the second block, the line 1 is actually making a channel. There's a TX transition, RX receiver. So you receive things from the TX. So the TX will be the line 4 is TX. The TX sends the message, and then from the 9 that is RX. RX will be receiving the message. So in the loop, we will wait from the MPSC channel to happen. So that this second to sixth line will be spawned in the background. It's background moving, and then it's not blocking. Immediately, it will print this photo, this line out, and then in the loop, blocking, because it's an infinite loop, and then it keeps pulling from the
mailbox. Mailbox.
Yes, Actor is one of the paradigm to actually deal with the asynchronous, but yes, this is something like Actor. Yes, but this is more fundamental. For the Actor, it actually needs to pass the message, right? It pass the message, and then the TXRX is actually one they call bridge to actually transfer the data out. Yes, yeah. Similar. Yes, it's how it works here. So we are dealing with the Docker runtime, and then there are some of the problems. But when we write like this, there will be some problem in it. When we are dealing with the low latency, but if you are doing with the web server thing, this shouldn't be a problem. Okay, that's one thing. We let the Docker to actually deal with the time. How do they pull the data? How do they process the data? What if there are a lot of Docker threads and there is only one CPU who does the job? So the Docker will actually help you to manage all the CPU time slice. They will have a queue of all these tasks, and then when you submit a task, they will maintain a queue. The queue is all those the task result slot. So whenever there is a result, you will write to this slot, and then tells the Docker, okay, this slot happens. Okay, what if in the same time there are multiple slots get written in it? The Docker will randomly choose one, and then pass it to you. So in the loop, you try to receive things, it won't be so precise, as in you get the result, it won't be so precise because Docker will handle it for you. And it depends on the Docker runtime's characteristic. Okay, so that's why number one is a problem, because we let the Docker runtime to deal with the pulling timeout times, and then to let the Docker to do the cancellations of the task. And then because Docker will do it for us, we want to bypass it. We will use the try receive, which is another not blocking function. So this wouldn't be this receive wouldn't be a sync function already. We use a try receive. So what the try receive does is it will pull the result and see, oh, it's empty. So empty, what we do? We skip it. So in a BC loop, we try receive things, keep pulling it, and then check the result. That's what we do. But this will have a problem because we bypass the waker. The waker is the one who listens to the kernel's file descriptor, the event FD. So now we bypass it, we need to pull. It will occur a system call called pulling. Keep pulling the kernel and tell us what is the result of it. So this is try receive. And then I got a parenthesis here. Beware of the syscall spam, because keep spamming the kernel. Second thing is you change the MPSC channel to the third-party implementation. Because why? From the first line, the Docker sync MPSC unbound is a part of the Docker runtime's implementation. It uses the Docker's waker to do a signaling, to signal the another end of the process that, oh, I already wrote one data in it, so you need to fetch it. Await got a notification, and then keep pulling it. So we want to eliminate this one so that our 8 to 12 line, this loop will be BC speed instead of await of the result. So there are a few data structure, this data structure. There are a few data structures that does this job without using a single wait, which is these two, dash map and a cross beam. And then me in my company who test these two implementation already, and then there are a few of the pitfalls in there when you are dealing with the low latency code, which is the first one, the dash map. Dash map is actually a concurrent hash map. It's just like a Java one, concurrent hash map. So when you are dealing with multiple threads, it will include the thread sharding. It will shard all these part of the hash map into different threads. So when you hit the cache miss, you need to check from another thread. It will incur a latency, which is unexpected. So we try to avoid it. For the crossbeam, it got a tail latency. So what is the tail latency? I need to explain the tail latency for you guys. Tail latency is like, you guys heard of the P99, P95 percentile or something? Not Pentium. It's like the P stands for percentile. So when we are talking about, the web, let's say HTTP request, it takes like average is 100 millisecond, and then sometimes you spike to 2 seconds. So the P99 is actually the max time we take it for the HTTP request. We say P99. P95 means the top 5% requests take how long. So the tail latency is actually the P95 to P99. So when we say there is a tail latency, means that there will be a spike of latency, which is unexpected from us. For crossbeam, this one, sorry. So this one, y-axis, sorry, the y-axis is the nanosecond of the time taken, and then the x-axis is actually the message, the number of messages. So we can see there are some spike of it, which is unexpected. So when we say tail latency is the latency of this graph, so this graph is enough to depict the idea of the tail latency. Okay, so for concurrent data structure, there will be a problem when we dealing with this. Okay, when we are doing the structural changes on the concurrent data structure, we will have to either block on the right side or the read side. That is confirmed because two threads are actually operating on the same data region. To either block the read, to tell the read, you block the write, and then you let the read operations clear first, and then you can start writing to it. Or you block the read, and then keep writing things. So in the interval of writing things, you can read. So will be some log or some atomic variables happen. In this case, the crossbeam doesn't introduce the log, and it introduces something different, which is the copy of the data. So it means you're writing things, and then you can keep reading it. But when you are doing the structural changes, let's say there is a B tree map, you go another level, you are changing the structure of the tree. So what happened? But you keep reading the things, and then your pointer changes. You allocate things, you need to swap your AVL tree and all this. So what happened? It will copy another copies of the tree and then keep writing to it. But your read is keeping reading this version. So until this finish, and then it will read this one, the second version. So it won't have log. It won't have the latency changes. Then you have to pin the thing. So when you are copying things, you basically have to manage the garbage collector. You need to manage the garbage collections of the copies because you keep writing things, and then if it changes a lot, it will create a lot of copies. So you need to delete all these copies. So the crossbeam does have the pin number 128, and then when you are dealing with the pin thing, you increment the number. So that is how it works. So the spike is actually caused by the garbage collection. Even though you are writing Rust, but you introduce a spike due to the EBR, epoch-based reclamation. You reclaim the copies of the data based on the epoch, based on the version number, EBR. Okay, so this is the pitfalls of this true data structure, and then the problem that we face when we are dealing with dog cures and all these things. As channel, MPSC channel stands for multiple producer, single consumer. You got multiple produce a message, and then you got one reader keep consuming it, keep dropping the message when you write the lead. Okay, we need something to pull the result and the system call. So these two problems is actually the pooling. How do we pull the data? And then how do we deal with the system call. So uring happens. So uring is a very new ways of dealing with the asynchronous, as I stated in the beginning of the talk. So what does the uring do? Uring is actually have two ring buffer, which is SQ, CQ, which is a short form of the submission queue and the completion queue, which is people will use this shorthand to represent these two ring buffer. So for this ring buffer, when you are dealing with the task, you need to submit the task. On the contrary of the Tokyo is a pool base, because I keep talking about pull the result. This one is a submission. You submit the task, and then you pull the data which the asynchronous operations finish. It will write to this completion queue. So you pull data from this queue. And how does it work is you've got the init params. These parameters is the parameters to create these two things, and then you call this function from the lib uring. You call this thing, and then it will occur system call 3 times. MF. With these 3 MFs is the SQ, CQ, and the SQE. The SQE is an array of the data which store all your operations. So MF is a memory map. A syscall to tell the kernel to give us memory region. So you use these 3 memory regions to create the SQ, CQ, and the SQE, which is an array of the tasks. And then the kernel will maintain the pointer to this CQ so that whenever the kernel finishes a task, it will write things to this CQ. And then you are the one who is responsible to pull the result from it. So how do we submit a task? We create an SQE, which is the submission queue entry, to call this function, to submit to it. And then what is the operations that support in this one? Basically, there's all the system call you can submit to it. It's like a proceeding. So we wrap the system call with all the parameters, all the arguments it needs, and then you submit to the SQ. Let the OS, let the kernel enter. You tell, now you already submit to this SQ, you tell the kernel to read it. It's like to put something in it, and then you tell the kernel, okay, you can start to process it. This is the uring enter. It will render the kernel. So when you are dealing with the WebSocket receive, when you want to write something, write, the SQE will be right. When you try to receive things, let's say you want to listen to a WebSocket connections, accept, get the file descriptor, then you submit another SQE, listen, receive. They keep receiving the data. So this is how we do in uring. A few moments later, then once the task is finished, so this is a CQ. From the CQ, you can pull from it. You can get the completion and then the simple loop to iterate this ring buffer, taking the CQE, which is the completion queue entry, taking all these tasks from it. So yeah, easy pulling. So you will have a trick to easy pulling, pull all these data out. You don't necessary to pull the kernel. You don't need to make a system call to the kernel, tell them, hey, when is this task finished? No need. You just take from this one. And then if there is no, then the loop will continue. Yeah. And then the structure of the CQE in Rust that is quite complicated because I read from the code. It's quite complicated and it is a wrapper of the C libraries. So right now you have to read from the menu, the Linux main page and all this to get the actual CQE. But here I am, I compile it for you. So if you look at the main page or the source code of the Linux kernel, it's actually it's that simple, it's this. And then for the user data, is actually the unique ID that's set by the SQE, which is the one set by you, the user defined one. So when you submit the task, you have to specify the unsigned clicks number to it, and then the task finish, pass back to you, the user data, you based on it to index the task that you created. And then what if it is some buffers and all these things? It's not defined by the. And then got lost already. And then for the result of the task, when we repeat, it doesn't define here. When we repeat, then you need to read from the main page. Let's say you need to read from the main page because it only gives you the result and the flag. So for let's say we want to receive something, at the main page for us, you try to receive something, and then this is the you based on the flag, you do the buffer select the flag to get the thing you got in the buffer. What buffer is it? So this is the buffer pointer. So you have to give it a buffer to it. So you need to allocate it yourself and then pass the pointer to this operation and do. Basically, this is a system call, which is very low level, and then it's not meant to be used by normal developer. And then for us, there is one wrapper functions in Rust that you can do. So it takes the flag and then returns you a number, which is the number of the buffer site you need to get. Okay, back to this. So this is how we query the result from the kernel. So why is it so important, and then why am I keep emphasizing it? Is because the layout of this IOU ring is actually represented by this graph. So this is the user's, the left side is the user space, and then the right side is the kernel. So whenever you are the one who set up this IOU ring, you actually create SQ and the CQ. The SQ and the CQ on the user side, you can access it from the user side. Basically, it's a pointer. You can access to it without any logs, without any system call or anything. But the kernel does have the pointer to this CQ, and then the IOU ring instance does help you to manage this memory region. And then it's directly writing to this one, so you don't need to pull, you need to make a system call to pull the result from it. And then when you are looking at this, yeah, you can publish the syscall to the kernel, and then the kernel will help you to arrange all the system call. It's basically a serialization of the syscall. It's like a bus. It's like a bus. You tell the kernel to do stuff for you. You manage all these tasks together in a sequence, and then it will help you to finish it. And the result may be not in a timely manner, but you can actually pull it from the CQ. So, time so fast. Okay, faster, sorry. So what do we do? Because we serialize all this and then let the kernel to actually process this all, we reduce the context switch. The kernel don't need to switch to this kernel or switch to that CPU to do tasks. It's all single threaded. So we reduce the context switch. We reduce the system call because we got lesser system call to pull the result from it. And then we got 0 copy of data because the kernel is responsible to write things directly to the CQ. So when you are dealing with all these WebSocket connections, you are dealing with the RESTful and all this, you can create multiple IOU ring. You create multiple IOU ring, then you got 2 ring buffers you need to iterate. So when there are a lot of IOU ring, you basically become the simu which is the legend of king ring buffers. Yeah, is that efficient? It's like a joke in my company because I deal with like a lot exponential growth of the ring buffers. So I would call myself.
No, the basic issue like memory, access limit, like that.
Yes, you can actually use a command line to make it as high as you can. Basically, yeah.
You can adjust the size of the ring buffer.
Increase the memory.
No, not only memory size, but also the file descriptor limit, because you create a lot of file descriptor during the initial state. Yeah, which is you won't face this problem. Number. So that is how I got the information. There is one menu written by the Meta developer, which is formerly Facebook. He is the one, the main author of this IOU ring. So he does manage this website, which is quite easy to be Googled. If you type a lot of the IOU ring, you will get this page. Basically, my idea of the slide is taken from this. So this is the site very useful. It's like MDN for me. Whenever you got a problem with the IOU ring, you browse this and then you can easily Google it. No, my slide is not finished. So when I tell my bosses, yes, we already reduced a lot of system call, but unfortunately, there are still quite a lot of system call happens. It's nearly 0, but it's not 0. Why is it? And then I tell him that, okay, because here we receive things, and then it's only used once. The system call is only used once. So if you want to reuse it, we need to submit another call receive. Let's say we need to keep looping, keep receiving a message from a WebSocket connections. You need to submit this receive into this IOU ring. Keep on going, keep submit. And then whenever you submit it, you need to call this system call. IOU ring enter. So my boss tells us, why can't you be optimize it out? And then I said, actually, yes. So this is how I optimize the IOU ring. IOU ring mechanism, because IOU ring is so flexible, it can help you to optimize things. So these are the 3 methods that I use: 0 copy send, 0 syscall and hot and the buffer receive. So the first thing is 0 copy. So there is one API in the Linux called scattergather, and then in Rust term is in programming language term is the vector IO. So basically, you have maintained an IO vector of these things, and then what is it? It is like a pointer to a string. So when you try to send things out, there is a string, but you not necessarily need to pass the string to this system call. You can pass the pointer to this system call. What your string needs to be concat. Pass multiple string pointer to this system call. That's how the scattergather system call work. So yeah, there is a send message ZC. ZC means 0 copy. So we receive the IO priority things, so you can actually pass this IO vector to it. So IO vector is the vector of these pointers, so you can actually pass a pointer of the string instead of pass it. So because you pass it, you need to copy it to the kernel. First thing. Second thing, zero syscall in the hop part. So yes, because the thing I said, you need to keep enter the IOU ring to tell the kernel I already submit the task in SQ. You not necessarily need to do that because there is a flag called IOU ring setup SQ pool. When you set this, wow, your CPU usage must surge to 80 or 90 something. Why is it? Because that is the background thread helps you to pull the SQ in kernel. So no need to keep calling the not SQ, IOU ring enter to tell. It will have a spinning loop to spin in the kernel space, keep looping the SQ for you, the kernel states. So you no need to enter. Okay? And then there is one thing. When I use this, it still got the IOU ring enter, even though it is almost empty in the SQ. So I look into the menu, and then I see why. Because there is one parameter called SQ thread idle. This is a timer. So whenever there is no IOU ring enter, it will help you to do this. So you will set it large enough so the IOU ring instance will not help you to call the enter again. So that's what we do to make zero syscall. Another thing is the provided buffer. So provided buffer is a very new thing, which happens to be the last year feature from the X. I'm not sure how to name it, how to spell his name, but Expo. Okay. James Expo. He's the main author of the IOU ring. He does provide us the provided buffer feature. So provided buffer is like you receive things, but now you can get multi-shot receive. You receive, so you only need to submit one, receive multiple, so you can keep receiving all this. So you don't need to tell the kernel to keep. No. It's like you don't need to resubmit the receive in kernel. It will help you to do this automatically. So you can save more CPU instruction call, right? So it's quite complicated, and then I just tried it out. But what we got is the QPS increased about 6%, and then the latency also drops also. I don't have a benchmark of the latency, so that's the thing. So the user provided buffer is also provided by you. You need to map yourself and then provide a pointer to this system call called receive multiple to get all these things. So it's also residual in this space also. So what is the cons of it, provided buffer? The cons of it is you may be getting batch message because you keep receiving it in one notification. So you notified by the kernel. Oh, you pull from the CQ, yay! And then you got what? You got a batch message. So, and then it's very low level. So the first thing I got is why I can't deserialize it as a string. So yeah, you have to decode it because we are using WebSocket secure. You have to TLS decode it. So you decode it, you got the message, then see what you got. When the market is busy, we will get the batch message. You can see from this, but then you can see some of the invalid URL. Why is it? That is because of the WebSocket frame. The WebSocket does have the header, so you need to calculate how much length the WebSocket is to slice this into multiple message, and then you need to calculate how much length the WebSocket header is to remove the invalid characters. That's how troublesome it is. So yeah. The final part of this call is actually How are we integrate in the Rust? Because this is still a very native ways of handling the IOU ring. Although Rust does have a single way, but for Tokyo, as I said, it's pool based. But in this system, it's actually submission based. You not necessarily need to pull things. Instead, the way you submit things matters. So Rust does have some debate in the community, which is the async read, write, and the pull stuff. So I think you guys can actually read on the comments because for me, I'm not sure about what is the point of their debates and all this because their debate talks about how do they pull and read things, and then how should I explain to you? Explain this the IFC, the idea of IFC.
Request for comments. Like they want to get feedbacks on the design.
Yes, they need to get the feedback from all these users and all these the communities, and then their discussion will actually dictate how we write code in the future. So it is also quite new, and then quite new. Quite new. See, read. The debate is quite old lah. They talk about really long time already. I don't know what it means. Okay. So there are some traits in future they will be integrated in Rust to properly to suit this submission based asynchronous model. So let's see how they do lah. I can say this, but in the meantime, you can only use IOU ring like this, submit your things instead of the traits because it's not so mature in Tokyo, and then for Tokyo, the backend is not necessary IOU ring.
It's not only in the way the Rust only in there in the way the other programming language, not only Rust.
I think not sure in other languages.
So this CU, but it's much more mature, right?
Of course, man. The Linux is the C. The library is really in C, so it will be more mature. But in terms of the framework and all these things, basically it's not integrated in the Node.js, so you can't see in Node.js. Maybe Dino can. Maybe Dino have this.
I can call using FFI, right?
Yes, you can call it FFI, but how do we actually integrate? Because the paradigm of how you submit the async task is different than how Tokyo is. Oh, paradigm is different.
Are you asking for like the language support, doing support?
Language support lah.
Yeah, on IOU ring.
It's very low level. Ada yang high level lagi kalau lebih dia beauty pelan-pelan. So if you use any dia
I think .NET will be more mature because .NET they are using the Windows asynchronous I/O also. There's one called IOCP. IOCP is also submission based, so it probably more suitable more sure No need to have big changes in the framework and all this, and then can adapt to this more elegant.
Kalau nak guna tu dengan guna native library lah. So dia depends dengan library apa kau guna. Bagi contoh kalau orang guna .NET, sebab saya background .NET. So dia ada yang famous selalu orang guna third-party library lah. Dia macam tuan soft JSON. Tapi yang kita guna contoh sistem text JSON. So it's a library yang Microsoft official sendiri pun ya ada di punya terus so depan diguna lah. Tapi kalau terdapat di library selalunya dia tak berapa.
How does it translate? Because I already use the Linux specific implementation. So how does it translate across example, Rust is a platform.
Platform.
How do you translate from what you use?
Kalau dia compile to binary. So orang tahu. So
Like to
yeah,
what
that
is
specific system call. So different OS ada different system call dan different mechanism sebenarnya.
So for example, if they are implementing Tokyo, so it will use OS recipe.
Tokyo doesn't use IOU ring.
Docker doesn't use IOU ring, but basically the Docker is, let me see, executor reactor. So basically Docker, when you want to change it to multiple platform, let's say you want to make it in a BSD, or you want to make it in Windows or Linux, this is the one you need to change, because this one will wait this executor. All this higher level logic is still in Rust. It's not platform dependent, but the reactor is platform dependent, so you need to change code in here. But as I said, the way we pull things and wait things and then to pull from the kernel the result, how is it happen? The logic is not suitable for the IOU ring, because IOU ring is totally different. It's totally different. It's not pull from data. You need to have another, maybe the executor here needs to have maintain the CQ, keep looping, and then return to the task. Change it up. A lot of need to change.
Maybe I can explain a bit more as in, the IO, right? There are two types of IO. One type we call it poll based, like it mentioned is poll based.
Yes, this pull based.
And then the other one is completion based. The poll based we have epoll, KQ, and IO. Epoll is the one implementation in Unix based system, and Windows have their own stuff as well. Here, because Tokyo is the model of the Rust async await is based on more like polling kind of logic. So that's why here Tokyo uses the polling based systems. And IORing is the different mechanism which is based on the submission based. And the difference is that poll based you keep polling, submission based you submit a task, and then once the task is done, you don't and then you get from another place, which is like less system call. That's why submission based is faster, and then the polling based is you need to keep sending system call to get the result.
And then even for the async await syntax, the async await syntax, the syntax in Rust is actually based on the future task. So there is one library called future with S on top. Future Rust. Yes. So it's based on this one also. So this one does have the pull ready or not ready, which you won't see that in IOU ring, because IOU ring you got this result already. It wouldn't be not ready. It wouldn't be none. You already got this result. So all of the async await stuff in Tokyo is built on top of these futures. So if you want to reuse it, pretty hard lah. I can say that you not. So if you want to use that, you can't use the feature. Yes, I think my slides end here. Yeah, that's my company's name. Quad.
So is there any questions?
Yeah, so now we have Q&A session.
Q&A session. I know it's very tough. Yes, come.
So now you have two queues, one for submission or for completion. And okay, you submit something and you get it that it's done. And then you have to request another system call to get the data, right? Where is the data?
The data is you need to provide it. The data, let's say when we are dealing with the provided buffer, you need to provide this buffer.
So it will be like empty.
Yes, it's an empty array. It's an empty array. So you need to tell the IOU ring how big it is, how many slots it is. So whenever you receive a thing, it will write to this buffer. in one slot, one offset. Basically it treats as ring buffer. So it gives you this thing, and then in the CQ here, you've got the flag. So you need to buffer select the flag to get the index of where the data is in your user provided buffer. So you index from it, take it out. That is your data. That is your data, then you complete. Yes, this is how it works. Or if it's small enough, let's say just a single receive, you can get the data from the pointer, based on pointer. So you dereference the pointer, you get the data already. So it's also in the CQ. If it's small enough, it's in the CQ. If it's not, you throw error also.
What about the Romeo, which is a high level?
Yes. There is one Chromium. It's also a runtime. It's also a synchronous runtime written by the Datadog, which is, for me, is a very good startup and do the data visualizations. It also have a so-called runtime, but the runtime is actually different than the Docker. It also use IOU ring. Utilize IOU ring, so you can actually write a single await, but in the backend, it is using IOU ring to do the task, and then you just pull from you. So when you pull from you, yes, it will have a memory limit. So when you use this one, you have to increase the memory limit, max something like that, because it helps you to pull things, and then it uses a lot of memory to help you to pull things. To answer the questions, it basically have another layer to help you to pull things in this graph. It have an interpreter layer to do this for you. So whenever you get the pull ready stuff, you get the things. But the backend is IOU ring. 没问题 My bro. Question?
One more question, just wondering, I don't know whether this is a big idea or what. Because from what we know, when they write the constant thinking models, such as Metal Swiss, there's a huge traffic and almost even everything and unfortunately most of even they are not in the they are not passed into buy. So my question is this IO unit you just wondering, is this IO unit tend to solve the problem or what?
I would say it's probably like scaling problem. Scalability. If you have a scale, like there's 1 million concurrent users, and maybe you can scale your web servers to like maybe 1,000 web servers in a short period of time. I think you can handle those. I don't think it's like unless you want to cost optimize like your scaling solution, like I only want 100 servers, but I wanted to serve 1 million users. In that case, you have to like optimize every path that the backend travels. So maybe one example might be using library in some of the application, but I think the quick solution to like handling 1 million concurrent users is probably just scale your web server. Yeah.
I think this is a very good interview question.
The use case for something like this is more like where we cannot scale our hardware. Yeah. For example, like in play games. In play games, you cannot ask the players to open their computer. You have to open your game what. So that's when the IO whatsoever is coming up. You have to optimize at application level. But for like Taylor Swift whatsoever, they yeah, you need to have a proper software architecture no matter how professional, how good you are on optimizing your application, there is some limit like what you can do.
In this case, you don't really care about scalability, right? Just care about latency.
Yes.
Yeah. So it's because you're only just building an engine, it's just for your traditional to use.
Yes.
Yeah.
Correct.
So you just want to execute the tape as quickly as possible.
Yes. Correct. So I think it's also part of the optimizations where it can solve the Taylor Swift issue lah. So for the Taylor Swift issue, really I wish or whatever cause it is, okay, you need to pinpoint what is the problem. So when it starts to have like C10K concurrent 10K connections, then your server down, then you need to see, oh, I'm still using single connection, single thread, not single thread. One thread per connection, definitely will crash one because one thread you use like 4 MB of memories. You definitely will run out of memories. You need to solve this. After you solve this, then you see, okay, your connections will take a lot of like memories, or you take a lot of you keep pulling data. Yeah, you keep pulling data. So too frequent means slow. So you cannot handle a lot of users. So users will need to wait for your server to process all this. And then you solve it. You optimize by pinpoint where the problem is one by one to solve. And solve the biggest chunk of problem first. So this is one of the way lah. Maybe the ultimate way, because if you got that problem, I think there will be that you can change your language stack, you can scale it, you can put Redis cache to something else, so you need to query a database. A lot of optimizations you need to care of.
It's more like last resort lah, very niche.
Very niche. Very niche.
I think this is much more suitable in a real-time scenario use case, right? Can you say like if if there's some real-time computation needed to be done, for example, Taylor Swift, they want to track how many people bought the tickets real-time. Like they can go to the website, see now we have 100,000 of tickets sold real-time, and the number is legit. And those kind of scenario use cases, maybe you can use IOUring for that.
Real-time, whereas in my field is more like, press the brake, your car must brake now.
They do. Yes.
Question: how much faster?
I am not sure about how much faster, because if you want to measure how much faster, you have to actually look at the time, the kernel flag. They will have a time when does it receive. Because it may be because how do I say this one? So it depends on how so the time I observe is when I take the result from CQ. Actually, it is maybe seconds. Back then, the kernel write to the CQ. So I don't have any way to actually observe that timestamp yet. But we do have reduced the system call to 0 during the programming hot part, and then we natively compare from the 800 microsecond down to 8 microseconds. So it's like 100. 10,000% what is it called? Lower latency? Lower latency. Yeah. So I think that's a win for us. I think the biggest win is actually how we write the code, how we structure the code. That is the biggest win, because this is the pain point here. Other thing is just a bonus point. This is the biggest point when I'm dealing with a lot of conditions and keep creating the Docker trace and background trace, all this.
Why do you need to create multiple LU rings? Like why not one LU ring and then submit all the tasks, listens, throw there, and then
Good question. I'm that ambitious to make it as one, but for every ring you got a lot of system call there, right? You need to index all the wait, I forgot. For WebSocket, let's say for WebSocket, we will maintain the user data. Back then, we will maintain the user data. For user data, we submit the user data and then we identify it by the user data from the CQ. We will mess up because when I want to do the RESTful, I also use this LU ring. So I will mess up this. Better than I just create two LU ring instances, one to handle all these WebSocket connections, one to handle all the RESTful connections, RESTful and all this. It's better for me to create because create is cheap. Create one is just cheap, but maintain it.
You keep track of.
Yeah, you keep track of all the user data. Troublesome. Creating more is cheaper and then more easy to manage.
Any other questions? Oh yeah, there's one question.
I was wondering, like, the different, the main problem in Tokyo, like, one, and this one, right? So this one, Tokyo thread, is it same like we create the OS thread?
It's similar to create the OS thread, but the difference is we let the Tokyo will have to schedule this task. But when you do the OS thread, it will also OS does have a scheduler. This depends on you want the Tokyo to handle for you or you want the OS to handle for you. But OS is more expensive because OS will schedule CPUs, schedule all these contacts.
Okay, we do the syscall, I don't see like, so by using IO use uring, do we reduce the syscall to the kernel or just that depends on the situation? You get what I mean? The main point here, we want to reduce the syscall. Or
Yes, the main point is reduce the syscall, but in here we are not reducing the syscall. From Tokyo switch to IO ring is actually we reduce the context switch because for this one the Tokyo spawn, the Tokyo will come to this task, it will somehow pull from an internal state, and then it will come to this task, it will also pull from this. So when it starts switching this task, it will have a context switch also. Now, what I say is serialize the system call is because we're using one loop to handle all of this code to reduce the context switch.
I can explain more a bit about the Tokyo. The Tokyo spawn is a green thread. So Tokyo runs on green thread. The Rust setting await runs on green thread.
It's like go routine. Yeah, it's go routine.
And then and Tokyo there's another spawn. They call it the Tokyo spawn docking. Tokyo spawn is used for the IO based tasks, and then Tokyo spawn docking is used for the CPU based tasks. You know when you're writing performance sensitive code, you need to differentiate whether the task is IO bound or CPU bound. Let's say it is CPU bound, then you throw it into the spawn docking. Then spawn docking will spawn like a system thread. They'll use, I don't know whether they'll spawn another system thread, but most likely they'll use a new system thread, AD thread, and then they'll run it there. And Tokyo spawn will spawn the green thread. Green thread you can spawn when it is very cheap because green thread is managed on the user space, and system thread is a bit more heavier to create. So IO-bound task you spawn, and then CPU-bound task you do spawn docking.
So I can gather from this, I have to go back home and open my OS book.
Yes. CSAPP. Start to read CSAPP, CSAPP.
I have to, yeah.
Oh,
This one, legend.
Legend.
many books. We have to go back again.
Guys, any other question? No question, then we'll probably end our talk.
Okay.
Okay. So thank you, zypeh, for this insightful talk. Right. So so now okay. So